this video. Share again. Share. Okay. Yeah, we get started. Oh, sorry. Yeah, I started to record. 3, 2, 1, ready? Let's go.
Maybe have Cindy do the first like title slide. That way she can just transition into her name, and then I'll do my name, and then you and
Yeah.
Mike can do yours.
Okay. Cindy, can you do it? Oh, sorry.
Yeah.
Maybe my can you do it? Because I think that Cindy will take the most of the slide.
So you want I take the first two
Yeah,
slides?
just briefly is a introduction about the projects and then who is the member, and then you start to the objective.
Do you
That's it.
want I talk about the objective answer or just the
No,
first slide?
just the name of our object and then the name of own member in the group. Yeah, and then you will continue to the objective. I think the objective even we take care of this and the overall design. You got it?
Okay.
Okay, ready?
Yeah.
3, 2, 1, yes.
Okay. Hello everyone. We are group 7. Today we would like to talk about oh my god. So can we start again?
Okay.
Let's start again. Everyone forgot.
Don't
I
worry.
forgot to stop already.
Don't worry, I will cut the video from here.
Okay.
3, 2, 1. Yep.
Hello everyone. We are group 7. Our group includes Cindy, Evan, Mike, and Quote. Today we would like to talk about the integration of parabolic trough with the thermal energy storage tank.
The overall objective and design requirements was to design a thermal system that collects heat from a thermal collector and uses that heat to thermally charge a thermal energy storage tank. During night use, this basically consists of having a solar trough, a TES heat exchanger, as well as a pump. This consists of basically a 2-loop system with respective valves at certain places to restrict flow in certain areas. For our overall design, we decided to mount the solar trough transverse in relation to the TES tank and heat exchanger. The reason for doing this was to ensure that basically maximum radiation can be had with the solar trough itself and not be blocked due to the TES tank and the heat exchanger. In addition to this too, we wanted to make sure the solar trough was able to be adjusted at varying angles to basically accommodate with how the sun sets and rises. So as you can see on the pictures on the right, you will notice basically a spring-loaded pin and a welded plate that sits inside the TES tank, as well as supported by basically just a square hollow tube. And this allows for some adjustability in that. For our overall design, the overall design requirements were intended to have a good amount of serviceability as well as functionality. Hence, this design uses 6 ball valves at points 5, 10, 20, 19, as well as 22. This is basically to make sure that anywhere throughout our pump pipe system, we're able to restrict flow at any point, as well as to make sure that they're accessible at all areas of the overall footprint of this to make sure if something catastrophic happened, we're able to shut it down quickly. In addition to this too, I decided to use two globe valves, or sorry, two check valves. These were intended to basically relieve pressure any time we have a variation in material change. So most of the pipe consists of stainless steel, while the copper piping at 0.23 will be our check valve, and this is just basically intended to relieve pressure before having a change in material, which will be the copper tubing through the solar trough. In addition to this too, are basically, sorry, next slide. For our overall cost, it was broken down into three categories, basically the licensing and equipment costs, foundation costs, as well as the overall piping system costs. The categories include basically our part costs, labor costs, basically whatever that equated to per hour, per feet, per whatever unit. Taxes and logistics set at 12% to basically work with a relative 9% tax rate in addition to just shipping and logistics, and then also the estimated time and sizing for each respective part. This set us to a grand total of $40,932.58.
Now we move into the solar trough. The solar troughs is concentrated energy sources that harnesses raw heat from the sun. This can be done by using a series of the parabolic mirror to focus sunlight onto a small area. And the receiver tubes was placed at focal point of the parabolic mirrors and blackens on the outside surface to increase absorptions. The parabolic trough system can use in this project is a long parabolic curve mirror to focus sunlight into the thin receivers at the focal points of the mirror, which is suspended over the centers by the mirror of the support system. This tube is filled by the terminal 72, which can be reached temperatures high at 450 Fahrenheit degrees. And the liquids used in these designs of terminals, which run through the TES to heat up the motor source in the TES. And in the additions, the oil pipelines is covered with the layer of the protection glass to trap the reflected light inside and increase the efficiency of the heat absorption for the light pipe. And it also maintains the durabilities of the tubes and reduce the light reflections loss. Sorry. In short, sorry. Yeah, I'm done with this. Mike, can you?
Next, I want to talk about the thermal energy storage tank. During the day, the heat that is generated by the sun is being stored into the thermal energy storage tank. And usually we use the molten source meter to will heat it up. And at night, when the sun is down, it will be used at the main source of the heat and the power plant. In this design, we just use the 1.5 inches schedule for the stainless steel for the tube, and the footprint of the tank area is 4 feet by 4 feet. And the tank is being designed with the 10 layer, and each layer is includes 6 patches. Next, please. Inside the tank, for the recycle short meter, we're using the part figure to estimate the thermophysical property of the fluid, and we just then we can to calculate the diffusion length and thermal diffusivity based on the two equation. As you know, like in the each layer is include 6 blocks that are 2 meters in length, and the diffusion length is directly impact the diffusion. The thermal diffusivity directly impact the diffusion length. That would also affect the spacing between 2 adjacent passes of each layer in the tank and the piping system. The material with higher thermal diffusivity respond faster to the change, and this results in require less number of tubes and bend in each layer. Next, please.
All right, next we'll talk about the pump type. Calculations for sourcing this pump will be talked about later, but for now, I'll introduce the model. We chose a high head, high efficiency circulation pump, which is also a centrifugal pump that is rated for water, coolants, and oils, specifically ethylene glycol, which we would use to model our system after, given its similar fluid properties to thermal 72. The maximum flow rate of this pump is 40 gallons per minute and rated for a maximum feet of head at 75 feet. The maximum viscosity is 17 centipoise, which is more than enough for the viscosity of the fluid that's running through the system. And it can handle temperature ranges from 0 to 250 degrees Fahrenheit, which is well within our 0 to 140 degrees Celsius range for a working fluid.
The heat transfer calculations. These overalls here, I already draw the diagrams of the heat transfer when the sunlight beam go from the sun and go reflects on the trough and go into to transfer the heat into the fluid. And in short, the incoming solar energies is absorbed by the glass layer, and the energies went through the absorber tube by conductions and transferred to the terminals by convections. And by the way, the remaining energies is transmitted back to the glass by convections and radiations. And over here, you can see the radiations goes out of the tube. And the energies from the radiation and convection then pass through the glass layer by conduction then, and the energies absorbed by the glass layer would dissipate to the environments by the convection and radiations. So I already made the calculations, and the output temperatures of the terminal 72 was defined is roughly around 142 Celsius degree, with this useful heat transfer at about 4.2 kilowatt. And by considering the small divisions of the control volumes when the terminals go through the pipe of the TES, I state out here is the equations of the balance equations, and I use these two equations to determine the energies balance and the temperatures increase of the salt when the terminals go through the TES is about 7.5 Celsius degrees per second. And the capacities of the TES was defined at 112,000, is mean 112 kilowatt.
All right, next, I will talk about preliminary calculations. So in our simplified system, the unknown variables of our scenario include volumetric flow rate, optimal pipe diameter for the system, excluding the TES, which is given, and the specifications of the pump required. Ideally, the optimal flow rate of the system can be determined by using the heat transfer computations Kwok introduced earlier to establish a relationship between pipe diameter, inlet and outlet temperature. However, such a complex mathematical model calls for the use of computational modeling software such as EES. Therefore, under our simplified and narrowed scope of focus, we have decided to start with an assumed volumetric flow rate to first obtain a probable optimal diameter for our piping. So based on various published research papers, parabolic solar collector systems call for low flow rates to optimize heat transfer. Based on what I've read, the mass flow rate is usually between 0 to 10 kilograms per second. So for our initial calcs, we will assume a volumetric flow rate of 50 gallons per minute. So over here, I have a couple tables detailing calculations based on known variables. The first table, we have thermal 72 fluid properties. We have density, kinematic viscosity, and also dynamic viscosity listed out. And then it is given that the pipe sizing of the TES is 1.5 inches nominal, schedule 40. So from that, we can look up the chart of inner diameter, area. We can calculate the length based on the number of passes, and the total line length inside the TES is 73 meters. And below that is another table detailing piping specifications for the solar trough, TES, and the remaining system, which is basically the piping between the TES and the solar trough and the heat exchanger. So now we will look at preliminary calculations for economic line size. For this table, we can see that we have input volumetric flow rate of 50. And based on comparing the fluid properties of thermal 72 to those of more well-known, we found that thermal 72 closely resembles that of ethylene glycol. So we use that to reference the economic velocity based on table 6.2 on the left. So the economic velocity range is between 1.2 and 2.4 meters per second. From there, we can calculate the range of area that we are looking for. Based on these calculations, the economic line size comes out to be 2-inch nominal, schedule 40. Next, please. Next, we move on to mathematical modeling of the system. So the entire system can be modeled based on Bernoulli's equation, which is basically P1 over rho g plus V1 squared over 2g plus Z1 equals to that repeated at the second point plus head loss due to friction and minor losses, and also head of the pump. This equation can be revised and rearranged to solve for pump power and also model the total change of head in the system versus Q to find the system performance curve. So here on table 7 lists out all the minor losses based on the CAD model shown earlier. We have all the components listed out, and the total minor losses come out to 41.48. And now on the bottom on table 8, we have pump power calculations based on 50 gallons per minute. So at 50 gallons per minute, we have a pump power of 551 watts, or otherwise 0.74 horsepower. Now for the pump selection, based on the calculations table 8, we started sourcing a pump that is capable of handling high temperature fluids, compatible with synthetic oils, such as ethylene glycol, and capable of handling high viscosities, and is rated at 1 horsepower. We size up just for margin's sake. So from McMaster, we sourced this Series 60s pump as shown earlier, and based on the specifications of this pump, the max flow rate is only 40 gallons per minute. Therefore, we redid all of our calculations based on a flow rate it can handle. And for this, I chose 35 gallons per minute, which translates to 2.4 kilograms per second of mass flow rate. So here we have finalized calculations. Table 9 is a revised calculation for economic pipe size at 35 gallons per minute. From those calculations, we come up with the conclusion that the optimal pipe size is 1.5 nominal, schedule 40. And at 35 gallons per minute, we have a pump power requirement of 0.56 horsepower. Same as before, we size up for margin's sake. So we look for pumps that are rated for 1 horsepower. Next, using the modified Bernoulli's equation shown previously, we can model the system performance based on various volumetric flow rates versus the system head. And here we have a graph showing the system performance curve based on gallons per minute versus delta H in feet. Now, using the pump that we sourced, we looked at the pump performance curve and then superimposed the system performance curve on top. And we can see that at our chosen volumetric flow rate of 35 gallons per minute, we find that it is within 50% efficiency of the pump. Now, keep in mind, you can see that this pump is not all that efficient. The max efficiency is only 52%. But based on all the research articles published and comparisons to other similar pumps out there, we found that pumps usually have low efficiency for low flow rates and have higher efficiencies for high flow rates, like 100 gallons per minute and above. So we selected this pump based on the fact that it has the efficiencies within the 50% margin. And this is for a Series 60s model, impeller speed at 4.5, I'm sorry, impeller size at 4.5 inches, and speed at 3,450 RPM. And now we come to the bill of materials based on our calculations and sizing of components. We have all the piping, all the fluid system components like check valves, ball valves, T-joints, elbows, bends, and all the necessary fittings. All the components sourced have female MPT fittings, therefore we had to source male MPT fittings to connect to the piping. The piping we chose will be flared at 37 degrees, therefore we will use AM fittings to conjoin the component with the piping itself. Therefore, we also have AN fittings, including nuts and sleeves. And the total cost of all the components comes out to be $23,651. And McMaster was chosen as the preferred preferred vendor over others based on their availability and available inventory and low lead times. If we were to order from McMaster, most components will come within 2 weeks. All right, and thank you for watching, everyone.
Yes. I think we're doing good.
Do we want to give it one more run through?
Do you want that?
I think this will be good. Let
You
me check.
sure?
Oh, I think it's about like 20 minutes.
Huh? What?
Yes.
Yeah.
I have now like 17, but I lost the first part, so I think it's around 20 minutes.
Shit.
What can you stop recording?
Oh, sorry. It's no
Oh my
worry.
God.
I will cut it out. I will cut all of everything else.
So what do you guys think? So